Good afternoon, everyone. You just open the chat here. I hope everyone can hear me very clear. Okay. Let's wait for a few seconds here. I see a lower number today in the attendance. Not sure if the recording of the lecture is okay. So how was the tutorial this week? Some of you already attended the problem analysis session. I hope it's useful. Yeah, there's a section today and tomorrow as well. Okay, perfect. Excellent. Yeah, we'll try to do our best to get you guys more, interacting with the TA and, get familiar a little bit when, on the topic. So I attended some of these groups, and I'm going to do this also during the whole semester, just to hear a lot of feedback about how you understand the material that we deliver in the lecture and what kind of misconceptions you have, and try to do our best just to help each other to get into more of understanding of the topic as well. 3% just showing up, right? Yeah, showing up, not the right words. It's participating, right? So yeah, participation mean here is really make use of this time, right? So if you have questions, you don't have to really feel like you are in an exam. You are not solving a problem in an exam. You're solving the problem with your friends, with a TA, if you have questions. So it's kind of yeah, and the 75% of the time, it's just a rough number, like we decided, because some people will log in and log out and stuff like that, or just make sure that you are most of the time actually attending the tutorial session. So far, I attended 2 sections. I talked to some of you guys, and I listened to some of the comment made in one of the tutorial session yesterday. People are asking about, the assumptions, and do we have to really write down the assumptions before we solve the problem? Even the assumption is actually doesn't make sense. It's already written in the problem, or stated in the problem statement and stuff like that. I wanna just bring your attention to something very important when you think as an engineer. Okay. Not all the problem that you're gonna face as an engineer will be written in a nice and clear format as you see in the exam or as you see in the textbook. Most of the time, actually, you are looking into something in the physical life, and you try to describe it. You try to put it, actually translate it from, something that you see, and you try to solve, or you try to fix, or you design, and then you bring it over in a piece of paper and start writing some, description of this problem, and you start putting some assumption on this, right? So I want you to think as an engineer, right? So I know the goal for many of you here, just to get the course and, get some grades and stuff like that. But the most important thing is to think all the time that what we are trying to do in this course here is just to get some fundamental understanding about the topic. How can we really think in the fluid mechanics? How can we approach problems and solve it, and so on? I know, sometime you're trying to jump into some conclusions, and some of you actually are, you are very smart, and they ask question about some of the problem that we are solving now about shear stresses and stuff like that. And I want to make sure that everybody's clear about this, that this fluid mechanics course is one course out of many in the fluid mechanics topic. And what we are trying to do in this year is just to scratch on the surface of the fluid mechanics, just to get some kind of general understanding on how we approach fluid mechanics. Having said that, none of the concept, none of the problem that we're going to solve, we're going to do some analysis by ignoring important things. So, but some of these problems can be analyzed much more precise, much more accurate, including so many other factors. But of course, because we are limited to the amount of time and also limited to the focus of this course, and we're not focused like on so many topics, so we don't get into so much details in many topics. Doesn't mean that we are solving, using a wrong approach, but you have to keep in mind that this is like, that's a very simple problem that we are trying to target, right? So even if we spend a lot of time trying to understand the problem, try to, put it in a piece of paper and put some simple analysis for this problem, it doesn't mean that this problem cannot be solved much more accurate, or like, I'm not, that's not the right term, much more in a much more complex way, right? So what I'm saying here is, I have heard some of the questions to the TA and some of the discussions, and I want to make sure that everybody here attending, he knows that we are trying not to be as hard in the beginning, not to just take one step at a time. We are kind of getting into the ABC fluid mechanics, right? And we are in the first chapter. So if we ignore something, if we don't get so much into detail of one topics, we mean this. We are actually, we do this, we plan for that. We're trying to get one step at a time. So just be patient and forgive us if we get so much simple at some point. Not everyone in the class will have the same kind of ability to maybe make more critical thinking about this topic. So this is just my general comment about yesterday's sections. So again, we're going to continue today talking about the surface tension and other property related to fluid mechanics. We still didn't get into really the hardcore of the topic, but to try to understand all this property and what does it mean and how can we use it in some of these engineering applications. So I'm going to share the screen with you here so we can start. Any question before we start? Yeah, sounds good. I hope you can see that. Let me open the chat somewhere here. Okay. So last time we talked about viscosity, and we had some problem on how can we use the viscosity from the shear stress perspective and do some analysis for simple engineering application. We're gonna get into another property today, which is important to many applications, and I will get into the application in a few seconds here. But the surface tension is defined only for liquids, okay? And what is defined here is the molecules at the surface of the liquid have a greater attraction for each other than they do for the molecular below the surface. So if you look at this diagram here, you will see all these particles that is inside, the fluid itself. It has like, some kind of molecular, forces that is actually bring these molecules together, right? So which mean that if you take like this, for example, particle, it's surrounded by so many particles around, and there are some attraction forces. You can say that the summation of force at any of these points is basically equal to 0, right? Which is 0 in the resultant force, but there is some forces actually between every particle and the other one, right? So every molecules and the other molecules. Now, if you get into like, those particles at the top of the surface, and I hope you can see my like writing here. So let me just use maybe another, right? So if you look at these particles here, right? So at the surface, it's not surrounded, so there's few particles are missing from the other side, right? So these particles are missing. That means that some of these particles will have a resultant force that is basically bringing, you know, these particles, or like, you know, making some tension of these particles in the direction of the depths of the fluid, right? So if you can imagine all these particles at the surface is acting the same way, so some of these forces is actually creating kind of, you know, a skin for these fluids, the shape, the surface, taking the shape of the surface. And we call it like, you know, a skin or a membrane, right? So you can imagine this is like, you know, a cover, like, you know, of these particles to the total, you know, material of these fluids. And this is what it means by the surface tension. So what is the ability of these particles in order to create this kind of membrane or skin at the surface of these fluids, okay? And this is basically like, you know, applied for liquids, and we can imagine that this is not, that cannot be said, you know, about it the same for gases as well, right? But for gases is like, you know, these forces is like almost negligible because, you know, the space between the particles is huge, right? And we're talking here about the molecular level. We're talking about small scale. So for liquid, you expect the liquid surface will take different shape, depend on the, you know, the interaction between the surface of the liquid and the material of this surface here, right? So you will see some liquid will go a little bit in this direction, right? Because there are some contact forces that is taking, you know, those particles and extended to this side of the surface, right? And for every fluid and for every surface, is going to be some kind of, you know, contact angle, theta, depend on the type of fluid and the surface energy or the type of surface as well, okay? So in general, surface tension is like a force only at the surface of the fluid, and it's acting in a certain direction. So the definition from a fluid mechanics perspective, we define these forces in a property table. And this property table is basically listing those forces per unit length, right? So it's asking you like basically to consider if this fluid is in contact with a surface. So at the edge of this fluid and the surface is going to be some length or a contact length between the surface and the fluids. And the surface tension given here will be force per unit length. And that's why you will see that, for example, for air-water surface, you will see the surface tension is 0.073 Newton per meter, okay? So surface tension force is always given per length, right? So, and that's why if we need to find out the surface tension force, we have to multiply the surface tension property by the length where the surface tension force is applied on, right? So this is a length that we're going to be always looking for in any of the problems. So one of the very simple, explanation on understanding the surface tension is like, when you see like mosquitoes or any bug that is, holding on the surface of the lake, right? And it can maintain some balance under, this condition. You will see it's basically standing as if the surface of the fluid or the surface of the lake is kind of, a skin or a membrane that this bug is standing on. And if you look at, if you magnify this section here and you consider the bug leg here is as a cylinder, right? So there's going to be some weight for this bug that is going downward, right? And at the surface, the contact between, right? At the contact between the bug leg surface or body here and at the fluids, there's going to be some forces here that is acting on this direction. Sorry, I just keep doing this. And this is what we call the surface tension force. So you can consider there are some contact lengths here and over here as well. So some forces is acting here in this direction. So depending on these lengths. So the surface tension force here would be basically the surface tension times these lengths here, right? And from this side, because this is just a cylinder, so the contacts between the cylinder and this surface would be another line here, right? So you can see this is basically Fs, which is sigma times L as well. Okay. Any questions? Everybody's quiet today, so no more discussion. I hope you can hear me well. Okay. Yeah. Why the length of the leg, right? Because if you look at this contacts, right? So this surface is stretched, right? The membrane of this liquid surface is stretched, right? So if you look at it from this side here, what you see the contacts between the surface and the fluids. Yes, some particles are here, but it's not actually stretching. That this is basically this piece here, which is holding the fluids. Let me just erase this and I will redraw it again. I'm going to exaggerate here a little bit and just use maybe this, right? It's almost as those particles here are holding the bug. Does it make sense to you here? It's almost like you have a surface now and this surface is stretched, right? And it's just holding this, leg, right? So in order to push it up, right? So it's basically, those particles here, the particle that is basically at the end is holding as if you are carrying this leg here. Does it make sense? Yeah, buoyancy force, this is completely different stuff. Let's talk about buoyancy force in next chapter, but it's a big, huge difference. We're talking about molecular forces here only at the surface, right? Buoyancy force is defined in a different way, okay? So anyway, so let's get back to our topic. So the surface tension is another property and is only concerned with the, the first layer at the top of the surface and how this layer is. Of course, if you put like something like very sharp, like a knife, and you push it inside this, it's not going to hold it, right? But if you put like a very thin wire and you hold it very nicely and you put it at the top of the surface, and under some condition this wire is very light, that is like, it's not like larger than the surface tension force, you can even put like a wire on the on this. But like if you are kind of putting like a huge body and this body is actually immersed in the fluid, this is where you're going to get into like the buoyancy force and so on. So we are not talking about like pressure forces and a body that is immersed. We are talking about at a molecular level. So this distance I'm talking about here is, you cannot even see it. So as you can see, the bug here is standing at the surface of the liquid, and it's like if this bug has a larger weight, it might sink and it cannot stand at the surface. And I have an example for you. When we do the analysis, we're going to find out how we can do this analysis now. So let's do the analysis for this bug here. And one of the things that is given in this problem that is telling you how much maximum mass of this bug will stand at the surface of the water. If if this bug is suspended on the surface and a bond, the surface tension of the water is not wetting the leg, and we're going to talk about wettability in just a few seconds. The bug has 6 legs, right? So you have, this is 1, 2, 3, 4, 5, 6 legs, and I'm looking at from the top. But if I look at from the sides, this is basically The bug is actually standing at the surface of this fluid. In contact with the water over the length of 5 millimeters is telling you that this bug is actually, you see here, it's the shape of the bug leg itself is actually stretching over the surface of the liquids, and the length or the contact length is 5 millimeters. So it's not standing at a point, as you can imagine, right? So now we need to find out what is the maximum mass in gram of this bug if we, in order to avoid sinking, okay? Of course, like you can imagine, if there is like a huge object or like a big animal is trying to stand on the top of the water, will not do that, right? Which means that we're not talking about like a large force here in terms of the surface tension. We're talking about a very small number of these forces, which mean that only the surface of the water can hold very little object as small as, like, bugs and mosquitoes and stuff like that. Okay, so how can we start this? I know some of you, like, will don't like to start writing these assumptions and stuff, but this is something very important, and you have to really train yourself into this. Every time you are reading problem, and as a part of initial analysis in your mind, just put the assumption, put like, what do you have for this problem, what is given in this problem, and what is missing, and how can we use this information in order to do some formulations of this problem, right? So we have the length of the bug, right? This is given. In contact with water is 5 millimeters, right? And this is water and a bug, and it's telling you that this is basically like, water. So we can, let's say, water at standard temperature of 20 degrees C, we can find out the surface tension of this water, right? If you go and the table A3, you will find that basically the surface tension is about 0.0728 or 0.73 Newton per meter. Okay, sorry, actually table A5. Okay, so what assumption we can make here? What assumption can FG spread over the 6 legs? Sure. Of course, the bug will be symmetrical, right? Anyone disagree with that? Yeah. Perfect. Water at 20 degrees C. Sure. This could be an assumption. That's no problem. So I can get the property at this condition. Yes. I like this, the force will be distributed equally on the legs, right? What other assumptions? The water is still, sure. But what is most important that it's still than the water itself? Yeah, the water, the bug, exactly, right? So the bug is under balance condition, right? Is stagnant, stopping at the surface, right? So even there is waves and stuff like that, that's not our concern now. We are trying to simplify things, right? But the bug is kind of stagnant, right? And the force will be applied on the bug will be basically distributed equally between the legs, right? So in order to get like, the total forces, we have to really, maybe look at a cross section here, right? So I can look at this cross section. Let me just do this. And when I mean here by the cross section, this is the leg, right? And I know that this contact length between the bug leg and the water is 5 millimeter, right? Gravity, that's right. You know, basically the summation of force will be 0, and the summation of force will be 0. Remember, like I know there is no difference between constant velocity and you know, a static type of things, because summation of force will be 0. But I want you to make sure that when you are writing something, it has to be correct. So we don't have motion here. So when we are talking about summation of forces equals 0, we are talking about static, we are talking about balance, right? We're not talking about steady motion or a 0 acceleration. So you have to really differentiate when you are writing this things, okay? Contact area. So I guess let me focus more on the solution here, because some people are doing some kind of, you know, comments here. But let's say that this is basically same way as we explained before. So this first layer here is stretched, right? So it's almost like you are carrying the liquid surface. Part of this liquid surface is carrying this leg here, right? And let's assume that this diameter here is D, right? So in this case, if I have, this is a, you know, the vertical direction Y, okay? So it's going to be some angle here, right? So theta, right? What do you think about one assumption that can simplify the problem? Because we don't have the material for this bug leg, right? So we're not doing any biology analysis here, right? So what kind of assumption in order to simplify this problem? Can we assume this diameter very small? We're talking about, you know, in our fluid mechanics course, we're not really concerned with molecular dynamics. So the length we are talking about here is like very small number. So D here is very small. Right? And when you imagine D is very small, if you can imagine now, this D over, like, you know, it will be basically shrink into a point, right? Right? So as if this cylinder shrink into a lens, right? It's a very small little point. So what do you think about this theta now? So small, exactly. It's almost 0, right? So as if this can be converted into a force, right? For each lens, which is, you know, this is F and this is F, right? So the force here is equal what? Anyone? Yeah, first we are talking about surface tension force. Right? It will be basically the sigma right? Times L times 2. because you have a force here applied over this whole length, and from the other side, you're gonna get the same thing. So it's basically 2 sigma L, okay? And the bug weight will be in this direction, right? But again, this is not the weight, right? The weight will not be affected at the leg. The weight will be affected at, so if you're looking at this now, and we're looking at the bug here, right? The balance, so theta is 0, right? So now in order to start the problem, so we can say that the summation of forces, no, it's not, is equal 0 as right? So now we have a force that is mg, right? And this is a total weight of the bug that is acting on the center. And this center could be an imaginary center, right? But now we have forces, right, over the 6 bugs, right? That is, each one of them is coming from the surface tension, right? And for each leg, we have 2, right? So we can say that this is for each leg, right? 2 sigma L. So if I need to do the force balance here, I can just take maybe, this is a positive direction. So now I know there are some forces here. So F leg, right? And there are some other forces, right? F leg for each leg, right? And we have 6 of these, right? So summation of force here will be mg, right? Minus, each leg has 2 sigma L, and I have to multiply by this by 6, right? And this will be equal to 0, which means basically I have static condition in this case, right? So in this case, I have m is equal to, I can just take this and put it on the other side. So it's 12 sigma L over G. And it's very straightforward. Here I can, why it is time 2 on each side, and I hope you can imagine this, like when we have a cylinder and the cylinder is, is carried by a small little surface. You can just look at it from both sides. You will see, like, a surface tension forces applied on this. So I have 12 here times 0.073 times L. L here is 5 millimeter. Make sure that you are using the same right unit for everything. So if this is 0.73 Newton per meter, so that means everything here has to be in meter as well. So this is 5 millimeters, so it is 5 over 1,000, right? Divided by G, which is 9.81. You can see this here as 0.00045 kilogram, right? Which means that we are talking about 5.45 gram, right? Right, less than 1 gram, right? Which is something you expect to get for this case. And so this is giving you an idea about, like, what kind of level of forces we are talking about here. we are talking about very small forces, right? And these forces is basically, we call it the surface tension, and you can imagine that this surface tension forces is very small, right? And that's why when you put a fluid in a cup, you see the surface is almost, horizontal, right? But if you are looking very closely at the edge of the surface between the liquid and the cup surface, you will see some kind of, edge at the stretch of the fluid over the surface. And this stretch is, yeah, grams. Yeah. I hope, okay, I'm not sure, I cannot follow all the chats here, but I'm trying to catch whatever questions you have. So everything's clear now? Yeah. Is it always 2 times? Let's wait and see maybe other application and see what is, how can we apply this? Remember, this is just an example of how can we use surface tension in some fluid mechanics analysis. Not everything is just about bug that is standing on the surface and the surface, the length of, or the contact length is in a linear motion, right? Or sorry, linear direction. So let's wait and see some other problem. Okay, so is that clear so far? Okay. So when we are talking about this surface tension, we can imagine, in the problem that we just solved, this is one of the applications when you're looking at the surface tension. But again, surface tension is involved in many applications where you are trying to define, the droplet, what is the droplet size, right? And this is very important when we are trying to design fabric, for example, that is the contact length between this fluid and the surface is very high, and then you will see some phenomena related to surface tension. We call it wetting and non-wetting condition. And surface tension is one element of the stuff, but the other thing that is very important is the energy of the surface as well. We are not into the material analysis in this course. We are just giving you an idea, at some point in some application, you will hear about surface tension when we are doing this analysis for this problem. So for wetting, for example, problems, you will see that this is the fluid is in good contact with the surface and is giving you this kind of angle theta here. And if this theta is greater, between the droplet and the surface, you will call it basically non-wetting kind of surface. Application for that is, as I mentioned, is like fabric, all the material that is water repellent, that you will see this, the surface tension forces are actually taken into account when you design the surface. Inkjet, all the printers, right? Remember particle dimensions, how, this particle dimension can be created by a nozzle that is injecting fluids at the surface in order to do this printing. The droplet size is a strong function of surface tension property. Okay. As I mentioned, many applications when you are talking about sprays, you are talking about surface tension is not the only property, not the only thing that we have to do in order to, characterize this spray or characterize these jets. But you will see as part of this problem, we have to really understand how the surface tension affects the problem, right? So when you are talking about injector, like gas injector in internal combustion engines, those injectors are designed in a certain way, and the different type of fuel will create a different kind of, size of these particle that you spray inside the combustion engine, which means that, evaporation of these particles, the heat transfer inside will be affected by the droplet size, okay? So when you are characterizing this droplet size, you will see some surface tension force that you have to consider. Same thing when you are talking about boiling, for example. So you see here in this picture here, you have, boiling process is, you are adding heat, and this heat is converting liquid into steam, and this steam will start by, having those kind of, you know, shapes of these bubbles, or right, and those bubbles actually maintaining some shape based on many forces. Some people were asking in the beginning about like buoyancy forces, right? Yeah, you can see here, this is inside the fluid. So this bubble here will be affected by some buoyancy forces, but also the way that it maintains its shape will be kind of some sort of course, this is very complex shape. But, you know, in order to maintain a certain shape, some of these forces inside this bubble will be part of it as a surface tension force. And in a few seconds here, we'll hear about new property that is also affecting this vaporization of this bubble. We call it the vapor pressure. But in general, surface tension force is in many applications, as I mentioned. So, and here I'm talking about, you know, boilers as one of these applications. I don't know if you heard about this capillary action and surface tension force in your high school, right? Did you hear about that? Anyone? No? Okay. Have you seen any thermometer, an old thermometer? Or some people, maybe they have in their house, like, you know, some thermometer you put on the wall or outside to see the temperature. And you see, like, you know, a very thin tube. Yeah. And those thin tubes that is, you know, carrying fluid, and this fluid is kind of, you know, expanding inside this tube to go, right? You know, sometimes you'll see this red kind of fluid, and depend on the temperature, this fluid will expand and it will go inside and indicate the temperature. So the design of this kind of thermometer, the old, the classical thermometer, is have to take into account in the design something called, you know, the capillary or the surface tension. And capillary here mean fluid will go in a small little channel with a certain length, right? So if you can imagine now, let's look at this here. You have a water and you have a tube like this, right? And the tube has a diameter D. And now fluid will go inside this, and it will go without any pressure, just like, you know, the normal atmospheric pressure here. The fluid will just go to this a certain level. We call it H. And this H here is, we call it the capillary length, right? But if you put, like, for example, mercury, you will see for the same diameter of the tube, the mercury is actually, you know, holding back from going inside this tube, okay? And in order to describe these phenomena, we are really looking into the molecular forces between the particles, right? The forces between those molecules inside the fluid. For the water and mercury are different. So the amount of forces between molecules in the mercury is much greater than for water. That's why, you know, liquid will be able to go a little bit inside this tube, but the forces between the molecule, which is, we describe it in the last few slides as the surface forces between these tubes, are, you know, much larger than the surface tension forces here. So in this case, you will see, like, you know, the mercury is not actually going inside, but it's kind of, you know, holding back from coming inside the tube. How can we describe this? Let's look at the, you know, a simple tube like this, right? It just give you an idea. How can we relate, right? So this is a tube, and this is fluid, and inside, you know, it's a liquid case in this case, right? So we have fluid that is moved to a distance h, right? So it goes here, and the surface is taking this shape here, right? So if I look at the, you know, what is actually bringing or pulling up this fluid inside is surface tension force, right? So imagine now I am holding the surface, and I am actually pulling this surface up inside this tube, okay? So what will be the surface tension force here, and which area or which contact? Remember, surface tension is force per unit length, right? So where is the lens in contact between the surface and the fluid? What can you imagine about this lens now? Let's look from the top. When we look from the top, we only see what for this tube? Not correct. Remember, the lens is diameter. Okay, let's first look at from the top. When you see this is a tube, okay? So it's a circular tube. So when you look at that from the top, what do you see? You see a circle, right? So you see, right? So when you see this circle, so the particle we're talking about here is those particles, right? Right? So, and those particles are, each one of them, it's holding part, like, you know, for every single small little L, there is a force coming up, right? Normal to the paper, right? For this lens here, another force and so on, right? This is what we see here. So this force here, it is coming because of these particles is actually pulled up, right? So the surface tension force here is basically what? Surface tension force will be applied over, not area. Okay, area is not even mentioned in this topic so far, right? We always talk about surface tension force as a force per unit length. It is basic, exactly, circumference, right? So circumference, like basically this is where the force is applied to, right? So it's basically when you are getting this surface tension force, right, is sigma times the length of action, which is 2 by r. So the surface tension force is basically, it's the sigma per unit length times the length where these forces acting, which is basically those particles pulling up. So this particle is pulling up the whole thing, is pulling up, you know, a volume like this, right? Because we said what you know, the fluid will go by the act of this force, right? So it's actually pulling this. So imagine the first particle is stretching, you know, to the top and is holding the other particle, and the other particle is holding the bottom particle. But at the total, in order to go a little bit with this distance, h, right? It is holding this whole volume or whole weight of this fluid, right? So when you are looking now on the analysis for this element, what do you do? So you have this element now. Right? And this force is acting in this direction. And I know many people will make mistake about saying 2 multiplied by 2. That's not 2. This force here is acting over the whole length, right? And the total will be sigma times 2 by r. Okay? Now this force is with a certain angle theta, right? And this force is holding this weight. And the weight here is mg, right? Or m is density times volume times g, right? So I can say the mass here can be replaced by density times volume. Why I'm doing this? Because I need to get the mass as a function of, you know, how much volume is going up here. So this is h here. Okay. Now, in order to find out the capillary length, this h here, how much length this fluid will go up. How can I do this analysis here? I can make the same assumption as I made before, right? This is theta, this is like, right? The most important assumption now is fluid is static now, right? No motion, right? And the summation of force will be equal to zero, exactly, right? And if I'm going to take this force, this direction as positive, the positive direction for the forces, I can now say that what the first force? Anyone? I'm looking at the chat here and see, like, somebody will help me to do this. Yeah, mg is in this direction, in the opposite direction, so it's going to be negative if I'm taking this as my positive direction. So I can say that exactly. So it's basically the surface tension force F sigma minus mg equal to 0, right? And I can take this m sigma now. I know that force sigma is 2 by r. This is the length times sigma, right? And remember, 2 by r here is not 2 because the 2 is 2 forces. No, 2 by r here is a circumferential, right? The circumference, right? So it's basically the total circumference. So it's 2 by r sigma minus an mg. I just need to get it as a function of h. That's why I put mg as rho times the volume, and this is volume. Right? So it's rho times the volume. And now I know the volume of this element, right? So this whole element is, the volume is what? The area, right? By r square times h, right? So now the volume here is by r square h. And then I have the g here equal to 0, right? I can divide the whole equation by pi. I can divide the whole equation by r. So I can just take this square here, right? And I can rearrange things. So h here is equal to 2 sigma cosine theta. I'm sorry, like I think I forgot. Yeah, f sigma here should be f sigma, right? I put it here and then cosine theta. Why? Because this is the direction of fc, right? So this component here will be f sigma cosine theta, right? Let me rewrite this here. Let's put it. Okay. So I can just say that basically 2 sigma or rho g r. Right?
Excuse me, I have a question.
Yeah.
For this problem, are we assuming that the area is like small enough just to consider it to be like a single point, so we don't have to consider the angle?
No, we cannot do this because this is a tube, right? The tube has a diameter, right?
Okay, so we have to consider the theta? Okay.
Yeah. So in this case, we have a tube, and just go back one step, right? Because we're talking about, like, those capillary tube, the small little tube that we see in the thermometers and stuff like that. We still see some liquid inside, right? When you're looking at, the scale of the thermometer for measuring temperature, you will see a level of the fluid inside this tube, right? So the tube has maybe, small diameter, yes, but still, like, it's some diameter, right? So now Theta could be zero, like, for a very specific fluid, right? And very specific surface, right? So you might see, like, for example, for water and glass, theta will be zero, even as in the property table, right? In this case, would be cosine would be 1. That's fine. But in general, like, whatever material we have and whatever fluid we have, we still have this theta there, right? So what I'm saying here is, like, you will have this H is equal to 2 sigma cosine theta over rho gr. When you calculate this actually in real life, for example, for water, you will see that H is very, very small. Like, you will see that this H in meter 0.00 something like meter. That means it's like, less than 1 millimeter or something like that. That's why capillary lengths will be different for different fluids, right? And you will see its function H is, no, it's not writing. Yeah, for some reason. Yeah, Apple Pen is like, doesn't like me. Do you mind just closing this and just putting it back? This is a kind of technical problem you never expect, right? It's connecting. Okay. Yeah, my God, that's not the best. Okay, so what can I do now? How can I write down this? So H is, any idea, guys? Anyone who's expert in the iPad? Looks like I have to really restart iPad, right? Okay. Let me stop sharing here. As notation. Yeah, I just like, okay. Let me try to reshare again. The notation in Zoom is not the best. Yeah, that's a good, yeah, I think it's back now. No. Okay. Let me share with you the PowerPoint on my computer.
Excuse me, sir.
Yeah.
I think someone said you might have the eraser selected instead of the pen.
Yeah, I tried to change it, but it's kind of like it's frozen. So the whole thing is not really.
Oh, okay.
Yeah, let me see now if it's gonna work or not. It's like, oh, it's keep asking me about, install the software, and I keep ignoring this because I don't have time. That's why, yeah, it looks like it's coming back again now. Let me share now the screen with you. Hopefully it works. Okay. Yeah. Yeah. It's better to update before you get into the lecture, I guess. Just like, yeah. Yeah, now we are back. Perfect. So what I'm saying here is like, you see this edge here? Oh my God, it's not coming back. I don't want to waste your time on this, but
Maybe might be that your pen has low battery, something like that.
it's 88%.
Oh, okay, never mind.
Yeah, I think I have to restart the iPad, but
Yeah.
Anyway, let's open another the stuff on the computer so we can continue our lesson today. And okay, stop sharing this. So you can see that, right?
Yep.
Yeah. And so you can see here, basically, like, you know, if you remember, h is equal to 2 sigma cosine theta divided by rho gr. Okay, and let me just put my iPad as a restart so I can, maybe you will catch this later on. Okay. So until I restart my iPad, I can just talk about this. So you can see here, h here is proportional to 1 over r, right? Okay. Yeah, it's giving me a message to install. Yeah. Not now. Yeah. I totally understand how you guys sometimes face this technical issues. Because even though, like, I tried everything before I get into the lecture, and still, like, you know, getting all this, you know, stuff. Then why it doesn't allow me to do this? Okay, so h here is basically proportional to 1 over r, which means that in this case, if I have a larger tube, what do you think about this h? Lower, right? The more the diameter of the tube is, basically the smaller the h, right? And that's why you don't see this problem when you are talking about, like, you know, a diameter of, like, you know, a few millimeter or even larger, like a 1 inch or something like this. You don't consider really the capillary action when you have a big tubes. When you have tubes like 5 millimeter, something like this, right? You only see this problem and you see this distance, right, of the capillary length only when you see, like, you know, when you're talking about, like, you know, a very small little tube, like, you know, we call it a capillary tube in this case, like, you know, 0.1 millimeter or even less, something like that. And that's why when you are talking about the porous in any surface, like, you know, even the tissue that you are using, and if you once you put, like, you know, tissue at the top of, like, you know, a droplet, you will see this kind of, you know, absorb this, you know, droplets. And why this is happening? Because the porous material, the porous of this material is actually, say, yeah, tree is like another example for this, right? We're talking about the capillary motion inside the plant, for example. You know, the force that is driving this liquid inside, you know, inside the plant tissue is coming from the, you know, capillary action. Okay. Let me, I don't know, it's even this. Now, even the mouse is not, okay, let me see here, install. Yeah. Okay, so you see now everything is frozen in my computer. Nice. Downloading something. Sorry, guys.
Maybe, sir, sorry. Do you
Yeah.
have Chrome open?
It's actually just like, it just needed to update something on the computer. That's why.
Okay.
Yeah, yeah.
While I have you here, do you mind if I ask you a question?
Sure.
In the last slide in figure B, there was there's a gamma in the.
Yeah, gamma here is like the Rogier thing, right?
Okay.
Yeah. So you can say that this is basically, this Rogier here. Remember, like, gamma is weight divided by the volume, right?
Okay, yeah. Thank you.
It's basically mg, right? Divided by v, which is basically rho g. Okay. So let me now, it's restarting my iPad. Hopefully things will work this time. I found the issue. Yes. Okay. You'll be surprised to see that, to know the reason. It's just this small little thing in the bin has to be screwed inside. Unbelievable. Okay, so let me stop this share. And let me just share my iPad now. You see this now? Perfect.
Yep.
Perfect. So we'll keep going like this. So now you see this edge is basically proportional over the radius. So only when you are actually talking about tubes that's small, you will see this edge is actually big. And that's why you're only concerned when you are designing, for example, something and you need to take care of like the capillary force or the capillary length in the tube. You are only considering this when you have, for example, like, a small little channel, right? And of course, this is very important when you are actually designing, as I mentioned, thermocouple, for example. You have to make sure that you account for the capillary action, because you remember when we were talking about the thermocouple, the expansion of the fluid is expanding, liquid is expanding with temperature. But now you have to consider, like, okay, now what is the length inside the tube before even the expansion, before even temperature change, right? So this is giving you an idea about, like, when sometime we consider capillary action or the surface tension force. Same thing I mentioned, another example for this is when you are creating, like, designing fabric and small channel kind of thing. For microfluidic, for example, like, it is a huge topic that is only talking about microfluidic, when people are like using this for testing, like taking sample of blood and taking this blood sample and creating a flow of the blood without even any machine. It's just like you are putting your finger and then liquids will go through a very small channel. So the force that is pulling this blood into the cell where you are actually testing this blood is driven by some kind of capillary forces or surface tension forces. Okay. Another example here, I'm not going to solve it, but just give you an idea about every time we look at different problem, we look at different condition. For example, last time we were talking about tube, right? And this tube has a diameter and the surface tension force is acting on the circumference, right? And we are getting this surface tension force. Now, if I'm giving you this example here, this is a problem, I guess, in your textbook, or it could be also in the problem set. What do you think about the forces here, if you already consider similar analysis that we've done before? Now we have, you see this part here. And this could be the surface tension force. And this will be the weight, mg, right? Can you tell me now what is this surface tension force? This is two plates. That's not a tube. Okay. What do you think the length affecting, or the force is actually affecting, the surface tension force is affecting on which length here? The two sides, exactly, right? So not all the time it is basically, similar. Like, for example, the bug leg is basically a cylinder that is attached to on two sides of the outer a tube that is basically circular shape. Now we have two plates. Now we are talking about 2 times, if this is length and it's not given actually in this problem. So derive an expression for the capillary height of H need to be determined. The angle of the surface tension force is given here as theta. For two vertical parallel plates, the distance apart, W. So this is, let's use a different symbol for the weight then, because W here is given as the width of between the two plates. So let's consider mg here as the weight, and this is basically the fluid, right? Okay, and this is H, right? 3-dimensional. So I don't know what that means. Yes, it is 3-dimensional. So this is the depth of the paper will be a distance that it's not even given in the problem, right? As figured. What will be H if the water at 20 degrees C and W is 0.5 millimeters? So yeah, just need to find that expression first. Okay. The fluid is water, right? But let's solve the problem and find out the expression first before even getting into the small, detail about getting the number. Okay. Now, mg is the mass, could be the density times the volume, right? Times g, this will be given, right? The volume here is what? This fluid, right, has a certain volume, which is, we have to assume this distance, right? Yeah, length, that's fine. L or B or whatever, simple, right? But this length is not given in the problem, and maybe, maybe we don't need it, but let's assume that this length vertical to the paper is B, right? So in this case, I can write down this mg in terms of density times volume, And the volume here is simple, is W times H times B, right? This is a volume, and then multiply by G. This will give you the total weight of these fluids. And the surface tension force here is 2, because both sides, right? Sigma. This is the surface tension force per unit length. And now the length applied over this surface tension force is, anyone? Which length here? B, exactly, right? So we have 2 sigma B, right? And we have this angle theta. That means if we take the summation of force in this direction, we'll get the same kind of analysis that we did last time. So in this case, we have the balance here. The summation of force would be 0. So if you look at this is a positive direction. So F sigma minus mg is equal 0. F sigma is 2 sigma times b cosine theta, right? So this is a component of the force. I didn't even talk about the horizontal component. What do you think about the horizontal component? Does it really matter to us in this case? Cancel out, right? And even if it's not canceled out, right, in other type of problems, right? What do you think? Like, you know, we are actually talking about, like, you know, the balance in this direction. So we are not really concerned with the horizontal direction. We are only concerned, like, you know, the vertical direction, right? So in this case, we have 2 sigma b cosine theta, right? Minus WHB, this is a volume, rho times G is equal to 0, right? It looks like, you know, very simple here. I can divide by B, right? Because B here, right? The whole equation divided by B. So B is actually doesn't matter. And that's why sometimes in many applications like this, we consider, like, you know, unit lengths in the vertical direction, right? So in this case, I can really say that this is H will be basically 2 sigma cosine theta divided by rho G W. And W here is the width of this channel, okay? I will let you handle, like, you know, the numbers here. So if you go to, like, you know, in this case in water, and you will find out H for water, you will find theta also for water will be, for this surface is 0, right? So for water, and let's assume here complete wet surface here mean like a glass or something like this, because it's not given in the problem. So theta can be 0 in this case, right? So you have sigma, which is 0.072, and W is given as 0.5 millimeter. You can find out H. I didn't calculate it myself, so but you can do this, right? So you can complete this. Okay, the last topic that we need to talk about today, I know it's we spend a lot of time on this technical issue, but just before we finish here, just if you give me like 1 minute, and this is very simple, last part of the lecture, we're talking about something called vapor pressure. And vapor pressure is another property I don't think we'll maybe, like, you know, even solving problem on this vapor pressure, but you have to understand vapor pressure is a very important property for so many applications. And when we are talking about vapor pressure here is the pressure at which the liquid is evaporate without increasing the temperature, right? So in this case, you know, what is actually evaporating? Like, what is the effect of heating, you know, on a fluid? The effect of heating on the fluid is giving energy to those particles. And as those particles start getting more energy, start to separate away from each other and try to, you move away from the fluids. And of course, those particles that will first move from the fluid, those at the surface of the fluid. So first particle will move, and then you'll start having this evaporation process. But vapor pressure is defined in general for any liquids it is basically equal to the pressure at which the fluid will evaporate even at the standard conditions, right? So we're talking about like, the temperature here is 20 degree or 24 degree. What will be the pressure at which the liquid will evaporate by itself? And you will see here, this value is different in this chart, depend on the temperature. Of course, we know that, for example, water at the standard condition, right, which is 100 kilopascal, will boil at 100 degrees C, right? But can the liquid evaporate at lower pressure? Lower temperature? Yes. If you are actually reducing the pressure, you can reduce the temperature at which the fluid will evaporate. Why this is important? This is just a table S3 that is giving you all the property here, right? Why this is important to understand this? Because in many applications, especially for pumps, right, you are basically taking the fluids from one side, increasing the pressure in order to deliver to the other side. And you have a rotor here that is converting mechanical energy into, like, we call it pressure energy. We'll get into the details in chapter 10. But the idea here is many equipment will reduce the pressure in order to make this suction, right? So pressure can reduce to a point where, like, liquid will evaporate. What happened after that, when the liquid evaporates, you start having some bubbles here. And as you go inside this pump, this bubble will, the pressure will increase again, and those bubbles will disappear under something called cavitation action. Those vacuum, like, the bubble will be generated here, and then, once it's here, like, the pressure outside of this bubble increase. So what happened in this case, the bubble will collapse, like, removing a space inside, and that's why we call it cavitation, right? So if the liquid evaporate under this pressure and now start like condensing again, like the bubble condense again, you will convert those bubble into, a small little size that create vacuum. And what happened in this case, the liquid around this bubble will kind of hit, the material. And you can see here in your right side here, this is the effect of cavitation. Why is that? Because all the liquid around this bubble will rush inside this cavity that is created by, like, the disappearance of this bubble. So, and those liquid keep hitting the material over and over and over. That is basically creating some kind of material damage. And we call it, like, damage due to cavitation in pumps. So what I need from you to understand at this point here is not all the liquid will evaporate at the 100 degrees C, for example, at water. You can actually, you can reduce the pressure on this liquid, and you actually can create the vapor out of this liquid by reducing the pressure instead of increasing the temperature. The pressure at which the liquid evaporates at your whatever temperature that you're looking at we call it the vapor pressure. I will stop here. I know I took so much of your time, but I'm sorry about, like, the technical problem I have today. And next time we'll talk about, chapter 2. Okay. Any question, guys?
May you go back to the last table?
Sure.
Thank you.
Not this one, right?
No, that one, please. Yes, thank you.
All right.